All right, so for our next example then, let's integrate the function 1 over 4x squared plus 12x plus 10. Which certainly is not an integral we can do by any of our earlier techniques. It's not an elementary integral. Of course, we can't split it up according to the sums, because the sums are in the denominator. U substitution is no good here, because if we let u be the denominator, its derivative would be 8x plus 12, and we don't have a linear function present anywhere here to go into the differential. It's a proper rational function, so long division isn't going to accomplish anything. But because we've got that quadratic expression in the denominator, that suggests that maybe this is an inverse trig type integral, and especially there's no square roots around, so maybe this is an arctangent type integral. To figure that out, we're going to complete the square on that trinomial. And this is exactly an example of what I was just talking about at the end of the last video. Yes, this is a quadratic expression, but it's got a leading coefficient that's equal to 4, not just 1. So let's just pull that 4 out. Then I'll be left with an x squared plus 3x plus 10 over 4, which is 5 over 2. And now we're basically going to ignore that 4 for the next couple of steps. We're just going to concentrate on this quadratic expression that I've put in square brackets. That's where we will apply exactly the strategy for completing the square that I outlined in our last lecture. So that means, first of all, I'm going to take the two terms with the x's in them, the x squared plus 3x, and I'll section those off with their own set of brackets. And then in particular, I look at that coefficient of x. It's positive 3 in this case. So I cut it in half to get 3 over 2, and I square it. 3 over 2 squared is 9 over 4. So I'm going to add 9 over 4 in the round brackets, and then I'm going to subtract it outside the round brackets. But notice all of this is still happening inside the square brackets. So again, we're basically plucking this expression out, completing the square, and then we're going to put the result back in. So as usual, this expression in round brackets now, we can factor this. It will always be x plus half of that linear coefficient, the coefficient of x, all squared. So in this case, that's x plus 3 over 2 all squared. And then we just resolve that constant. 10 over 4 minus 9 over 4 is plus 1 over 4. I guess in this case, rewriting it as 5 over 2 didn't really get us anywhere. But we couldn't have known that at the start. And so we wind up with 4 times x plus 3 over 2 all squared plus a quarter. At this stage now, there are 2 ways we could proceed. We could simply say, all right, well, if we come back up to our integral, now we're going to have the integral of 1 over this expression. That's a common factor of 4, so I could pull that out. And that's an entirely reasonable thing to do. It does mean, though, that now we're dealing with a couple of fractional expressions here. And it's not that that's a bad thing, but fractions do naturally tend to lead towards a bit more frequent computational error than integers do. So something that we need to be a little bit careful about, because this is also going to be a source of potential error, but can frequently give us nicer numbers in the end to work with when we actually go to integrate, is to multiply that 4 back in. Let's do this in a couple of steps. In principle, this is kind of straightforward, but I know it's one of those things that if you're not careful, it just so easily leads to mistakes. So we'll have 4 times the first term, so 4 times x plus 3 over 2 all squared, plus 4 times a quarter. 4 times a quarter is just 1. So that's nicer than a quarter. But then we can also bring that 4 inside the power of 2. But we got to remember, we don't just suddenly multiply 4 into the brackets here. The fact that this is being raised to the power of 2, that matters. So we have to remember that 4 is equal to 2 squared. So we've got 2 squared times x plus 3 over 2 all squared plus 1. And because now these are both being raised to the same power, now we're allowed to multiply those bases together. So 2 times x plus 3 over 2 is 2x plus 3. So we'll have 2x plus 3 all squared plus 1. And now that's the simplest form to put back into our integral. So let's see then. That means that the integral we can rewrite it using what we've obtained by completing the square. So instead of 1 over 4x squared plus 12x plus 10, now we've got 1 over this expression, 1 over 2x plus 3 all squared plus 1. And that looks a lot more like an arctangent type integral. We've got something squared plus 1. So in fact, this looks a lot like an arctangent integral where that constant k is just equal to 1, the simplest version of that integral. Now, we do still have to deal with that 2x plus 3, though. So we do this by u substitution. We're going to let u be 2x plus 3, which means that du would be 2 times dx. And so a half du is going to be what will replace the differential dx. And so now we've got the integral of 1 over u squared plus 1 times a half du. Of course, the half is a constant factor. It can come out. And now we're all set. We know the integral of 1 over x squared plus 1 would be 1 over 1 times the arctangent of x over 1. So it means that this is just going to be a half times the arctangent of u. Plus c. And as always, with any u substitution, we'll substitute back in for u. U is 2x plus 3. So in other words, that's a half times the arctangent of 2x plus 3 plus c. Let's do another one of these in the next video.